Your fishing hook might be acting like a battery, and certain fish can feel electricity. That sounds like a bold claim, but it is grounded in peer-reviewed biology, documented commercial fishing history, and electrochemistry that has been understood for decades. And once you see how these three things connect, the gear at the end of your line starts to look a little different. 5,000 years ago, the Egyptians were crafting fish hooks out of copper. Not bone, not wood, not stone. Copper. For a long time, historians assumed the reason was straightforward. Copper was more workable, more durable than organic materials. Clean explanation. Everyone accepted it. Everyone moved on. But here is the question that took decades to ask properly. If it was purely about durability, why did copper repeatedly emerge as a frequently selected early fishing metal across Egypt, Scandinavia, the North Pacific, and the Bronze Age Mediterranean? In multiple regions where copper was available and accessible, it became a consistent early choice for hooks and lures across cultures with varying levels of contact and exchange. That is a pattern, and patterns like that usually have a deeper reason underneath them. The reason began to emerge in the 1960s, and when it did, it quietly changed how scientists understood the way certain fish perceive their environment. Stay with this, because what comes next may change how you think about the material of your terminal tackle. In the 1960s, a team of Dutch scientists studying shark behavior observed something that initially made no biological sense. Sharks were driving their snouts into the seafloor, targeting fish buried completely beneath the sand. Fish they could not see, could not smell, could not hear. The sharks were locating something invisible: electric fields, microvoltages generated by the contracting muscles and moving gills of prey hidden out of sight. The biological sensor making this possible is a system of fluid-filled pores called the ampullae of Lorenzini. Research has documented its sensitivity across multiple species, capable of detecting very small voltage gradients in surrounding water. Exact figures vary by species and experimental conditions, and the research continues to develop. But the underlying capability is well established across peer-reviewed literature. What matters practically is this: certain fish can detect electric fields that no other sense can perceive. And the moment you absorb what that means, the material of your terminal tackle becomes a slightly different question than it was before. The ability to detect electric fields is called electroreception. And before you assume this is a shark-only capability, here is what the research actually shows. Estimates in the scientific literature suggest roughly 10 to 20% of fish species possess some form of passive electroreception. The range reflects variability across studies and how electroreception is defined and measured. That includes species every freshwater angler regularly targets. Catfish, rays, and numerous species from the order Siluriformes, armored catfish, Mandi, Jundia, are documented to carry electrical sensors embedded in their skin. Every time a fish contracts a muscle, every time its gills cycle, it generates a small voltage signature in the surrounding water. An electrical fingerprint that electroreceptive predators can potentially read at close range, in murky water, in low light, through conditions where vision becomes almost useless. The signal is always present in living prey. The fish that evolved to read it are always scanning for it. Now hold that fact in mind, because what happens when you consider the materials on the hook you are already using? When two different metals are placed in water, something begins to happen. Water, especially mineral-rich freshwater or saltwater, acts as an electrolyte. Two dissimilar metals in an electrolyte begin exchanging electrons. This process is called galvanic reaction, and it produces a small but measurable voltage between the two metals. It operates on the same fundamental principles as a battery cell. A copper hook in contact with a steel swivel sitting in the water at the end of your line. That combination produces a micro-galvanic reaction. The voltage generated sits in the millivolt range, small, but in species with electroreceptive capability or even heightened lateral line sensitivity, small additional cues in low visibility environments may matter, particularly in murky water after rainfall when every other sensory channel, vision, surface disturbance, scent diffusion, is partially compromised. This is not a claim that copper guarantees catches. It is a suggestion that the material of your terminal tackle may be producing an electrochemical signal that most anglers have never considered. And there is nearly a century of practical fishing history that points in the same direction. For close to 100 years, commercial fishermen in the North Pacific, both Japanese and American anglers working deep-bottom fisheries, used copper tube jigs. The design is almost deliberately simple, a copper tube filled with lead, hook attached at the bottom. These jigs produced flounder, rockfish, and large bottom species with an efficiency that comparably priced conventional gear struggled to match for decades. The standard explanation focused on mechanics. The jig drops, hit structure, vibrates, mimics injured baitfish, triggers a strike. That explanation is partially correct, but there is a second factor worth examining. The galvanic reaction between copper and lead in the presence of salt water produces a weak, continuous electric field around the jig. That field does not imitate the movement of prey visually. Under the right conditions, it may produce an electrical signature that shares characteristics with living prey, the kind of signal electroreceptive fish have been orienting toward for millions of years. Whether that mechanism fully explains the jig's long commercial reputation is difficult to confirm through controlled study. But the chemistry is real, the commercial history is documented, and the overlap between the two is worth examining rather than dismissing. There is also a registered United States patent built on this principle, a fish attraction system using a stainless steel hook connected to a zinc or aluminum ring, specifically engineered to generate positive voltage in water. The patent documentation describes tuning voltage output toward specific species. Whether such patents reliably translate to real-world fishing advantage under varied field conditions is a separate question from their existence. But their existence confirms that electrochemical fish attraction has been taken seriously enough for legal and financial investment, which tells you something about how the underlying concept has been evaluated in certain quarters of the industry. Now, back to the historical pattern. The Norse were crafting copper and bronze spoon lures between the 6th and 11th centuries. Archaeological excavations across Scandinavia have recovered them. The Egyptians used copper hooks 5,000 years ago. Civilizations across Cyprus during the Bronze Age selected copper as their primary fishing metal. It is worth noting that copper was among the earliest workable metals available to early civilizations. Its corrosion resistance, malleability, and durability made it a practical early choice. Some trade and knowledge exchange did occur between regions during these periods, so the pattern reflects both availability and selection rather than pure independent invention. Still, the repeated convergence on copper across fishing cultures, separated by significant time and geography, suggests more than simple availability alone. Then something shifted, and it had less to do with copper's performance and more to do with economics. The Industrial Revolution brought mass-produced steel to market at a fraction of copper's cost. For a tackle industry scaling to reach millions of anglers, steel was the rational manufacturing choice. That is not a conspiracy. That is straightforward economics. When a cheaper material performs adequately for most applications, industries shift toward it. Copper did not stop working. It stopped being the most cost-effective material to manufacture at scale. The modern tackle market does operate on product cycles, soft plastics, electronics, seasonal gear updates. Copper wire wrapped around a hook is inexpensive and durable and does not fit neatly into those cycles. Whether that influenced any deliberate decision is not something that can be verified. But the economic incentive is real and worth naming honestly rather than framing it as suppression. The American manufacturer Mepps, one of the more respected lure companies in the world, has quietly produced copper-bodied lures for decades. A company spokesperson, quoted in an interview on copper.org, acknowledged that under certain conditions, copper outperforms other materials, particularly after heavy rainfall, when suspended sediment reduces water clarity. Here is what makes that observation interesting. Murky post-rain water contains more dissolved minerals than clear water, which increases electrical conductivity. Under those conditions, any galvanic effect from copper would theoretically be amplified relative to clear water conditions. While direct experimental confirmation of this specific mechanism is limited, the field observation from a company with decades of production data is a point worth considering alongside the underlying chemistry. If you want to test this yourself, and testing is always more useful than theory, here are 3 practical approaches. The first costs almost nothing. Take a piece of pure copper wire, 14 gauge, and wrap 3 to 5 tight spiral turns around the shank of any hook you already own. The copper contacting steel and water creates a live micro-galvanic cell. The voltage is small, but it is real, continuous, and present across every cast. The second is the copper tube jig, the same basic design North Pacific commercial fishermen worked with for nearly a century. Cut a 5 to 8 centimeter section of standard copper pipe, fill it with lead, attach a hook at the bottom. Drop it to a structure where large fish hold. The galvanic reaction between copper and lead handles the electrical component. The weight handles the vibration and bottom contact. It is worth running it alongside your standard gear across multiple sessions and drawing your own conclusions from the results. The third is a copper leader. Anglers targeting deep-running salmon and trout in the Great Lakes have used copper line as leader material for years, noted publicly for its density and sink rate. The electrical properties follow from the same electrochemical principles, though the practical magnitude under field conditions is difficult to quantify. One important practical note: at sufficient concentrations, copper ions released into water can be harmful to fish, which means surface area and exposure time are practical considerations worth managing. Partial insulation, coating portions of your copper with varnish or wax thread, and leaving only a controlled area exposed helps moderate ion release relative to water chemistry and exposure time. In lower mineral freshwater, uncoated copper works for a longer period before local concentration becomes a concern. The principle is straightforward: enough exposed surface to produce a signal, managed carefully enough that local ion buildup does not become a problem. Ancient fishermen could not have explained this chemistry, but they observed results, learned what worked through accumulated experience, and copper kept showing up across thousands of years of practical fishing. Now you have both the historical pattern and the mechanism that may help explain it. Whether ancient fishermen understood electrochemistry or simply observed that copper performed consistently under difficult conditions and passed that knowledge forward, the pattern across 5 millennia is coherent and worth taking seriously. The question is not whether copper is a guaranteed advantage. The question is how much it helps, under what specific conditions, and whether those conditions match the water you actually fish. Low visibility, high mineral content, species with documented electroreceptive capability. Those are the conditions where the chemistry suggests copper's secondary effect is most likely to be relevant. If this shifted something in how you think about what is happening at the end of your line, drop a comment. Have you ever fished with copper, even accidentally? What were your conditions, what species, and what did you observe? Real field data from anglers fishing varied environments is more useful than theory alone, and every comment gets read. And if you want to go deeper into the science and practical techniques behind fishing that most mainstream channels never cover, subscribe to Hidden Fishing. That is exactly what this channel is built for. Subscribe, hit the bell, and let's keep examining what the evidence actually shows.